Recall that the LED flash.c example flashed the heartbeat LED, which was on our RB pin 15, and we defined a macro called LD1 that was equivalent to underscore lat B15. We're going to use lat B15 whenever we want to write to the LED. We also had a configuration macro called config underscore LED1 that used our library configuration routine config RB15 as digital open drain output. Inside our main, we configured the clock. We configured LED1. We initially set the LED1 to 0, which means it was off. Then we went to an infinite loop that delayed before toggling the LED through each loop iteration. We're now going to take a look at more complicated examples of both LED and switch I/O. This example is going to use a push button switch to control the state of an LED. If the LED is on, then when we press and release the switch, the LED will be turned off. If the LED is off, then when we press and release the switch, it will be turned on. A couple of things about the configuration. Here we're using RB13 for the switch input, and we're going to enable the internal weak pull-up so we do not need an external pull-up resistor on this push button switch. We have RB14 is going to directly drive its LED. That means that when we write a 1 to the port, the external port voltage will be 3.3 volts, which means the LED will be on. If we write a 0 to the port, then the external port voltage will be 0 volts and the LED will be off. As with the LED flash code, we're going to write some macros to make our code both more readable and more portable. The config LED1 macro is going to use our library macro config RB14 as digital output. RB14 is going to be configured as a normal digital output. It is not going to be open drain. It will be able to both drive high and low. We're going to define LED1 to stand for underscore lat B14. This is going to be used to affect the LED1 state. When we write to lat B14, we're going to be changing the LED1 state. This macro here, config switch 1, is going to be an inline function consisting of 2 lines. The first line is going to config RB13 as a digital input, and then we're going to enable RB13 internal pull-up resistor. Finally, we're going to want to be able to read the RB13 state, so we're going to define switch 1 as underscore RB13. So if we use switch 1, we're essentially testing the state of the input RB13. We're going to write 2 macros that's going to tell us if the switch is pressed. If the switch is pressed, then that means that this is shorted and this input voltage is going to be 0, which means we're going to be reading a 0 here. And what we're going to want to do is we're going to want to test to see if the switch is pressed. So if switch 1, which is RB13, is a 0, then it's going to say this is going to return true, saying the switch is pressed. If the switch is released, then the switch is open and the pull-up resistor is pulling this to 3.3 volts, which means that internally it's going to be a digital 1. And so if our switch value is a 1, it means the switch is released. So we're going to use this macro to test to see if the switch is released. Here we have 2 solutions for this problem. One is wrong, this is incorrect, and this is correct. This is written in a rather naive fashion. We'll talk about it first before looking at the correct version. First of all, let's take a look at the I/O configuration. That should be the first thing you always do after you do your CPU configuration, is to configure I/O. So first of all, we're going to configure our switch 1. This delay macro right here, delay microsecond 1, what we're going to do is whenever our practice is going to be that anytime we enable a weak pull-up, we're going to always delay a little bit afterwards, in this case 1 microsecond. Give it time for this pull-up resistor to pull this guy up to 3 volts. Then we're going to configure LED1, our output, and we're going to initialize our LED1 to a 0, which means that it's going to be initially off. So at this point, we're going to enter our infinite loop. The person who writes this code says, okay, well, I want to toggle this LED when I have a press and release of the switch. So I'm going to, and I have a macro that detects if it's pressed. So I'm going to say this switch 1 is pressed. So if it's pressed, then I'm going to toggle the LED. Now, what does this actually do? Well, what this does is that as long as switch 1 is pressed, it's going to toggle this LED. A human is extremely slow compared to a microcontroller. So when the person presses the switch, this code here is going to loop through here hundreds, if not thousands of times, toggling this LED, and it's not accomplishing what we really wanted. Recall that what we really want is only toggle this LED once for a press and release. We need to wait for essentially two separate events. First a press and then a release before toggling this LED. So this is the correct solution here. The configuration is the same. The difference is in the while one loop. So let's take a look at this. First thing that we're going to do is we're going to wait for the switch to be pressed. So this is a loop here. This is an empty body. We have a semicolon here. That means it's an empty body, and we're simply looping here. And this is saying while the switch 1 is released, just loop here. So it's just waiting. We're waiting here while switch 1 is released. We're waiting for a human to press this. Once the switch is pressed, then this is going to be false, and we're going to exit this loop. At this point, we have this delay of 15 milliseconds. What is this? This is for switch debalance. We're going to talk about this on the next slide, but typically for a mechanical switch, anytime you detect a change in state and you're waiting on the change of state like this, then you want to wait for the switch balance to settle out. At that point, the switch is now pressed. So now what we want to do is we want to wait for it to be released. So here we have another loop, and we're going to loop right here. As long as the switch is pressed, we keep looping here, waiting for the release. Once the release occurs, we're going to exit this loop. We're going to delay for switch debounce, and then finally, now that we've detected a full both press and release of the switch, we can finally toggle the LED. So we toggle the LED, we hit the bottom of the loop, and we go back up again and we start again. Here we're waiting for a press. So while the switch is released, we're going to loop here and so forth. It turns out that mechanical switches can bounce, that is, cause multiple transitions when pressed. This is a scope shot of a push-button switch when it's pressed. Here it's being pulled high through a pull-up resistor. When we press, it's going to go low, but before it reaches a steady state of a low, it actually bounced one time. It turns out that in this case, it only bounced one time, and it's settled in about 500 microseconds. If a switch bounces or not, how many times it bounces, how long it takes to settle, all depend on how the switch is manufactured, its age, and several factors. Don't be surprised in lab if you take a look at your switch that it doesn't bounce. The way that we wrote the code in the previous slide, after detecting a switch state change, we don't want to sample it again until the switch bounce is settled. If we sample it too fast, then we could think that this is actually a release when it really is not. The switch is still pressed. So we want to wait for after we detect an initial switch stain, we want to wait until we're here when the switch has actually settled. Our default value of 15 milliseconds is plenty of time for waiting for switch bounce to settle. You don't want to wait too long because you don't want to miss multiple press and release events. It turns out that a human switch press is always greater than 50 milliseconds, so this is not too long. As with the assembly language, there's many ways to write C code to solve I/O problems. What we're going to do in this course is introduce you gradually to better and better ways of writing C code for solving certain I/O problems. One of the key techniques that we're going to use is going to be using state machines to a state machine approach to solving I/O problems. So for this problem of toggling this LED for each press and release of the switch, we want to detect two different input events. The first input event that we want to detect is a press of the switch. The second input event that we want to detect is a release of the switch. In a state machine approach, we'd like to use different states for each input event. So in this case, we're going to describe this state with a name that says wait for press, and what we're going to do is we're going to draw a decision box here in which we're saying, okay, as long as the switch is released, we're going to loop in this state. When it's pressed, we're going to transition to the next state. In this state here, which we're going to call for wait for release, what we're doing is as long as the switch is pressed, we're simply going to loop. When we detect a release of the switch, then we're going to do an output action. In this case, our output action is going to be the toggle LED 1 before we actually go back up to our top state. Now that we've described the action of this code in a algorithmic state machine chart form, we can then translate this directly to C code in a fairly structured manner. This is going to be our new solution for the LED toggle problem written in a finite state machine style. The first thing that we're going to do in main is declare a state variable, and we're going to call it eMyState. We'll take a look at this, how this is declared and how this is defined in a minute. We're then going to call a library function called config_basic. This function combines all the previous functions we used for CPU configuration in one handy function. It calls config heartbeat, config clock, config default UART, print reset calls, and prints out our hello message string in this one function. This is defined in pic24 util.c. Once we call config basic, we will then configure our switch and LEDs before, and then we're going to initialize the state variable to our very first state, which is going to be called state wait for press. Let's take a look at what happens now in our infinite loop. First of all is going to be this call to this function called print new state. This is a function that we've written purely for debugging purposes. When we're debugging finite state machines, we're going to want to know what state we're in, determining what's going to happen next. Since we can't single step our programs, the only kind of debugging information we can get is by printing messages out to our UART. This particular function is going to print a message out to the UART anytime the state changes. We'll take a look at this in the next slide. This switch statement is the key statement that's going to implement the finite state machine on this page. Here we have two states. So because we have two states, we have two cases here, one case for each state. Let's see what happens. When we get to the switch statement, we're going to look at this variable and we're going to say, what's the value of that variable? If it's state wait for press, then this code is going to be executed. What does this code do? It says if switch 1 is pressed, then change the state variable to state wait for release. If the switch is not pressed, then the state variable remains the same. Regardless, once this if statement is executed, we're going to hit this break statement, jump to the end of the switch statement, and then execute this delay statement. This macro right here is set equal to 15 milliseconds, so this is going to delay for 15 milliseconds, which is going to debounce our switch, and then we're going to call our do heartbeat code, which blinks the LED. At this point, we're going to go back to the top of the loop and do this again. This approach is fundamentally different from what we did with the previous example. Let's go back to the previous example. Here, when we executed this while statement, the code hung up right here, waiting for the switch to be pressed. While it was released, we were stuck in this while loop. Until the switch was pressed, we did not go any further. We stayed right there. In this code, we're always going through this loop. And we're delaying 15 milliseconds each time to the loop, and then going back up to the top. When we execute the switch statement, we're polling the switch. We're sampling the switch. We're checking the value of the switch. If it's, in this case, if it's pressed, then we're going to change this state variable. What this means is that we are only sampling the value of this switch every 15 milliseconds. Because for 15 milliseconds, we're hung up here in this software loop. Then we come back up here and we sample the switch. This is called periodic sampling of I/O. So this loop is periodically sampling the switch. The period of the sample is set by this time here, which is going to be every 15 milliseconds. In this example back here, we were reading the switch just as fast as the PIC could loop through this loop, continually checking the value of the switch. Remember that we have this delay because of bounce in the switch. So let's take a little closer look at how the sampling works with switch bounce. So our new approach is to periodically sample the switch every 15 milliseconds in our while loop. In our first solution, we were reading the switches as fast as the CPU could loop. Let's see how this works with switch bounce. Here's a diagram of a switch. Here's some bounce. Here's a settling time. Here's a long period of time after the settling time in which the switch is held down. So we're sampling the switch and we're trying to see if it's pressed. Let's assume that we sample here and we see that it's released, so that's fine. Here, let's assume that we're sampling and we actually sample right here on the very first bounce and we detect that it's released. Well, we're then going to go to the bottom of our while loop, wait for 15 milliseconds, which is going to be longer than our settling time, and the next time that we sample it, we're going to be right here when the switch is still pressed, which is consistent with our first reading. We're not detecting a false release, and so all is well. Let's assume that we sampled it back here sometime, saw that it was that it was released, not pressed. We sample it again. Let's say we actually sampled during the bounce time, and we see that we're sampling it when the switch is still is released, is high. Since we did not see this time all is well, we still think that the switch is released. We're then going to go to the bottom of our while loop, wait 15 milliseconds, and now we're going to be sampling during this long time period when the switch is actually held down and stable, and we're going to see that the switch is actually pressed. So that's fine as well. So we want the sampling period to be long enough so if we sample here, the next time that we sample, we're going to skip the false release and see that it's still pressed down. We also want it to be short enough so that we don't miss this stable period. We know that the switch press for a human is going to be greater than 50 milliseconds, so the sampling time of 15 milliseconds is short enough. So let's go back to our example. We now understand that we're continually going through this loop, waiting 15 milliseconds here and sampling this switch about every 15 milliseconds. If we're currently in this state here, state wait for press, then when we execute the switch statement, that's what we're going to execute. If it's pressed, we're going to change the state variable to state wait for release. We're then going to hit this break, go to the end of the switch statement, do our delay, go back up to the top. Now at this point, we've changed our state to state wait for release. So when we execute this switch statement, we're going to execute this case statement right here, which says, okay, if the switch is released, then we want to toggle our LED and again change our state back to this state here. What's going to happen initially, let's say that we loop through and we detect for the first time that the switch has been pressed, and we change our state to state wait for release. Then the next time through the loop, 15 milliseconds later, we're going to hit this state. Now at this point, we've only 15 milliseconds into the press, so when we check the switch, it's not released yet, it's still pressed. So we're not going to execute this body. We're going to hit this break, go down to the end, delay 15 milliseconds later, and we'll loop several times through here until the human finally releases the switch. Once the switch is released, and we're then going to toggle our LED and then change our state back to state wait for press. When writing your case statements, you need to be very careful to always include a break at the end of each case. If you somehow forget this break, what's going to happen after this code is executed, then it will go ahead and execute this code in addition to this code here, regardless of what the state variable is, and that can be a very difficult problem to debug. Let's talk about how we declare this state and what is actually inside this debug function. To declare the state, we're going to do a typedef enum. We can call this name anything we want. We just call it state. And in this enumerated data type, we're going to list states. We've used capital letters for our states, and we have this extra state we don't see anywhere else called state reset. This state reset here is simply used to give this variable here, elastState, a default value. We're going to use this particular variable here in our debug function print new state. Recall that the purpose of print new state was to print a message out to the screen anytime the state variable changed. So what's going to happen is when we call print new state, we're passing in our current state, and we're going to see, is this current state equal to last state? Well, let's go back to our code and see what this is the very first time we called it. Well, we initialize our state equal to our first state, state wait for press, which this elastState is initialized equal to this reset state. So the very first time we call this function, these will not be equal to each other, and so we're then going to execute this switch statement, and simply based on the state, we're going to print out an informational message. At that point, we're going to exit the switch statement here, and we're going to set our current state equal to our last state. Recall that we are continually looping through here, so the next time we loop through here, we're going to come to print new state. At that point, we're going to execute this code, and we're going to say, is elastState equal to current state? It is equal. We have not changed it yet, so we're not going to print out any messages. If we didn't have this check right here, what we get a flood of messages out to our serial port every time through the loop, every 15 milliseconds, and we wouldn't be able to tell what's going on. This is only going to print this message out whenever the state changes. let's see this code in action. I've programmed my PIC24 of LED toggle.c, which is the C project that implements the code we've just discussed and powered on the PIC24. I'm getting this message printed to the screen, state wait for press. What is printing out this message? Well, it's this function right here, print new state is printed out, and it printed out the very first loop that I went through here. E state was was equal to state wait for press. The E state last variable is equal to state reset. They were not equal to each other, so it went ahead and printed out this message right now. And now it's continually looping through here, executing this code each time to the loop, which is checking to see if the switch is pressed. Since it's not pressed, the state variable is not changing, so nothing is changing. It's simply looping through here every 15 milliseconds. Let's go ahead and change something. Let's go ahead. I'm going to reach out of sight, and I'm going to press the push button. At this point, I get this message state wait for release. Why did that happen? If I go back to the code, what has occurred is that I went through the loop and I checked to see is the switch pressed, and it was true. So then the state was changed, and it was changed to state wait for release. I went down through here, came back up, executed this code. This state is now different from last state, so I printed out the message state wait for release, and now the code is simply looping through here, executing this if statement each time. And what it's waiting for the switch to be released. I'm holding the switch down right now, so this statement is false. So what I'm going to do over here is I'm now going to release the switch, which I just did, and so now I'm back in state wait for press. What you also can't see, since it's hidden out from your sight, is that my LED turned from off to on once I had a press and release. I'm going to go ahead and press the button several times, and each time I get a press and release, the LED is going to toggle its state.